Today we're going to take a look at 4.5, which is the second part of optimization. So in this section, we're looking specifically at word problems. So I've kind of wrote out some of the examples here. So here we have an example where it says we have 1,000 feet of fencing to enclose a 3-sided rectangular field. So the idea here is, well, maybe one side of this field, say, is on a river or a highway, something where you're not going to actually need to fence off the fourth side. So maybe I have a diagram, say, like that. Or I don't know, there's maybe a river here. Okay, so then let me label the sides. I'd like to use X, X, and Y. And then let me see what information I have. I know I have 1,000 feet of fencing to enclose the field. So I guess what that would mean is if I add my two X sides with my Y side, that has to total my 1,000 feet of fencing. Okay, now the other interesting piece of information here is the fact that, well, we're interested in the maximum area. So I know the area of a rectangle is length times width, or X times Y. So my goal, let me clean this up a little bit here. My goal is to maximize this area equation, but right now it has two unknowns. So what I'm going to do is I'm actually going to solve my top equation here for, say, y. So that would be y is 1,000 minus 2x. And then I'm going to substitute that y value into my area equation. So in that case, I'm going to have, let's see, a equals x times, and then I'm replacing my y with the 1,000 minus 2x. So therefore, let's see, my a is 1,000x minus 2x squared. I'm going to write that as area as a function of x. And then I'm just going to rearrange in descending powers of x. So here I have a function that models, what does this guy model? This guy gives me the area as a function of the side length x. That's this guy here. Okay, so my goal is again the same. My goal is to maximize this equation. So I know that I can maximize the equation by looking at where the derivative, so a prime of x, let's see what that is. By looking at where is the derivative equal to 0, right? So look for critical numbers. So what is my x? 250? Okay, so what the heck does this represent and what am I looking for? So let me look back at the problem statement. So I'm looking for what dimensions will yield the maximum area. So I actually have one of those pieces of information then. I found the x value, okay? So now I need to know if I want the dimensions. Well, I need to also know the other side length then, the y side. So what if I go back and I use this equation here? Just substituting my x in there. So wouldn't that just be y is 1,000 minus 500? 500? In other words, what I'm saying there is that, remember, my sides, my 3 sides have to add up to that 1,000 feet of fencing. So if I have 2 of the 250 foot sides, that's 500 feet, and another 500 feet, I have my total of 1,000 feet. So then my dimensions, I just need to write those out. They would be 250 by 500 feet. And so these are the dimensions that maximize the area. If I actually wanted to find the maximum area, well, I would just multiply, right? I'd say the area is 250 times 500. So what is that? 125,000. That would be square feet. I don't think this question asked for that, but I could be asked. Okay, so here's another example. A rectangular box with a square base is to have a volume 10 cubic feet. If the material for the base costs 6 cents per foot, for the top 4 cents per foot, and for the sides 25 cents per foot, find the dimensions that minimize the cost to construct the box. So let's see, my rectangular box has a square base. So let's see, I've got x. Okay, then if this base is square, this has to also be x. But the box is a rectangle, so that means the height here is different than the width. So I'd have the base, both lengths there would be x, the height, let's call that y. And then let's see what I can come up with. Okay, so I guess the problem says something about, the volume. That was 10. The volume is 10 cubic feet. So I was looking for the highlighter here. Okay, so the volume, that's length times width times height, right? So in this case, well, the length is x, the width is x, and the height is y. So my volume would be x squared y. There's my first equation. The other thing we're interested in is the cost to construct the box. So let me see if I can come up with an equation for that. So I guess let me highlight. Here's my first equation. And then I'm interested in, well, the cost. So let's see how this is going to look. Well, let's see. I've got 2 of these horizontals, right? I've got a base and a top. So let me see how I want to set this up. Let's see. Let's make some more room. Let's say the cost. Okay, so I have to add the cost of the base, the cost of the top, and then let me see here. I've got, 1, 2, 3, 4 sides, right? Front and back and the 2 sides. So 4 cost of a side. So that's really the equation I'm looking at. So let me see if I can figure this out. So let's see. The cost to construct the base. Well, let me look back here at the problem statement. So the material for the base costs 6 cents a foot. So I'm going to have 6, but look at the base here again. So what is the area of the base? Well, the area of the base is going to be, well, x times x, right? X squared, x times x. Okay, what about the top? So let's see, the cost for the top, 4 cents per foot. So 4, and then let me look back at the figure. So the top again, the area of that is going to still be x times x, right? So x squared again. Okay, so 4, let me look at the problem statement. Let's see, the sides, the material is 25 cents a foot. And then the area of a side, well, that'd be length times width. That'd be x times y, right? So that'd be 10x squared plus 100xy. So I guess I have, my 1, 2 equations here. So then, let's see, my goal is to minimize the cost, right? But again, I have 2 unknowns. So I have to do a substitution. Okay, so what if I take my top equation here and I solve it for, say, y? Let's see. One piece of information I didn't put in there, isn't there? Look, the volume is 10 feet cubed. So this equation actually looks like x squared y equals 10, right? So if I solve for y, wouldn't that just be 10 over x squared? So now I'm going to take this guy and I'm going to substitute it in for the y here. So then what is this equation going to look like? C equals 10x squared plus 100x times 10 over x squared. So now this is my cost as only a function of x. So what is that? 1,000 over x? Or if you like, maybe 10x squared plus 1,000x to the negative 1. And then my goal is again to minimize. So that means I would want to then differentiate. So c prime of x, what is that going to be? 20x minus 1,000 x to the negative 2. It's 1,000 over x squared. There's that. So if I'm looking to minimize, I'm going to look again at where is c prime of x equal to 0. So maybe for that part, maybe I'll do an LCD. So I'm just thinking maybe it would be useful to multiply, say, by x squared over x squared here. Then what do I have? C prime of x, that'd be 20x cubed minus 1,000, and then I have an LCD. It's all over x squared. Okay. So if I set that equal to 0, well, I multiply up my x squared, right? So really I'm just looking at where is the numerator equal to 0. So I'd have 20x cubed minus 1,000 is 0. Therefore, x cubed is what? 1,000 over 20? 50? So x is the cube root of 50. So I have one piece of information. Okay, so let me look back at my problem statement. Find the dimensions that minimize the cost. So I have the x value. So let me get the y side then. So the y side, I'm going to use, excuse me, this guy. Okay, so this might not come out that pretty, but that's okay. So it's going to be y be 10 over the cube root of 50 squared. Okay, so what are my dimensions? Well, I mean, in exact form, it would be cube root of 50 by 10 over, I could write that 50 to the 2/3. And then these are in feet. So to me, that looks like a good answer. I did an estimate just for fun, and I got about 3.7 by 0.7 feet. So there's an approximate answer. Now I was kind of thinking for a second here, something else we could do. We could double check, cleaning this up a bit. Let me write this maybe in a different color. Let's see, double check that the x value we found, cube root of 50, is a min. I mean, as opposed to a max, right? So remember how I could do that? I could use the second derivative. So let's do that. So I left my first derivative here for reference. It's right here, right? So the second derivative would be 60x squared. Oh, I guess, okay, quotient rule. So let's see, I have a quotient here. I'm looking at the whole quotient. So derivative of the top, 60x squared times the bottom, minus derivative of the bottom times the top over the bottom squared. So let me clean some more of this up then. And so here's my x value, right? My cube root of 50. So let me just go back and see if I can simplify this second derivative at all. 60x to the fourth minus 40x to the fourth plus 2000x over x to the fourth. okay, so I have some like terms. So what is that? 20x to the fourth plus 2000x over x to the fourth. So I could even write that down. Let's see, that'd just be 20 plus 2000 over x cubed. Okay, so here was the actual answer to the question, right? So make sure you got that part. But then again, what I'm doing here is I'm just double checking that that x value actually gives me a min as opposed to a max. And I'm doing that using the second derivative test. So I'm thinking, okay, well, here's my x value now, right? But look at my second derivative here. So if I plug a positive value of x in here, I'm going to get a positive number, right? So that means my graph is concave up for all, for all positive values of x. In other words, all x values that are of interest here. Okay, so if my graph is concave up, then remember, what does that mean? That means I have a local min, which is what I wanted. And so indeed, these are the dimensions that give me a minimum. Okay, here's another one. By cutting away identical squares from each corner of a rectangle and folding up the flaps, an open box can be formed. Okay, I can kind of visualize that if I was to cut out these guys and then fold up, these sides, I would end up with a box, a rectangular box. Okay. All right, let's see what else this says. It says the rectangle is 16 inches long. Whoops. So that means this length is 16 inches. And then what else does it say? It says 10 inches wide. So this length is 10. Find the dimensions of the box that yield the maximum volume. Okay, so then I have to think about, well, what is this box going to look like? Or at least how can I label the sides of this box as far as once the sides are actually folded up? So maybe I call this guy here X and this guy X. Because look, it says identical squares. See? Identical squares. So that means that these guys all have to be the same length. So X for each of those. Okay, so let me see what else I can do. So this length then, oh, that's interesting. Let's go with this one. This length here would have to be 16 minus 2 of the x's, right? And then let's look at maybe this one here. So this one, this length here, would have to be 10 minus 2 of the x's. Okay, so let's see then. So once I actually fold my rectangle into this open box, let's see. So I need to write the volume. So the volume is going to be the length times the width times the height. Okay, so once I fold up the sides, let's see. The length is going to be that 16 minus 2x. It's a little hard to visualize. The width is going to be this 10 minus 2x. And what about the height? So when I fold up the sides, the height is going to be the length x, right? So it looks to me like that's going to be my equation for volume. So the volume is x times 16 minus 2x times 10 minus 2x. So maybe I should, I don't know, should I distribute the x maybe to one of these? So 16 minus 2x times 10x minus 2x squared. And then let me FOIL. So what is that? 160x minus 32x squared minus 20x squared plus 4x cubed. Get that right? So the volume as a function of x, let's see if I can rearrange. 4x cubed minus 52x to the second, and then plus 160x. Look and make sure I got all this right. So let's see, I had 4x cubed, negative 32 minus another 20 is negative 52, and then plus a 160. Okay. So there's my volume function. And then what was I supposed to be looking for? Yield the maximum volume, right? Look back at the problem statement. So my goal is to maximize this guy. So I'll find the derivative. 12x squared minus 104x plus 160. And then I'll set that equal to 0. Oops. 12x squared minus, that looks okay. Set that equal to 0. Okay, and then let me see if I can find a GCF. Let's try at least 4. 3x squared. What is that, 26 and 40? See if I can factor that. So, let's see, so what do I know? Well, I have a positive here, a negative here. So I guess both of these signs are going to have to be negatives. Let's see, multiplies to 40. I mean, there's 10 and 4. There's 20 and 2. And there's 8 and 5, etc. So I have to kind of try, so maybe I'll try, what if I put 2 here and 20 here? See what happens if I multiply this out. So that'd be 3x squared. That'd be minus 6x minus 20x plus 40. Oh, look at that. That gives me my negative 26, which is here. So it looks like I got that right. Okay, so then what are my x values? 20 over 3 and 2. So these are my critical numbers then. Okay. So now let's see, my goal was to maximize. So let me see, let me think about these numbers for a minute. So would 20/3 actually be a valid answer? Let me look back up here. So let's see, if x were 20/3, let's see what one of these sides would look like. Like what I'm looking at is I'm going, okay, like, see here on my rectangle, I guess that side, one side, you know, the width would be equal to 10 minus 2 times 20/3, which would be what, 10 minus 40/3? Well, 40 divided by 3 is more than 10. This is a negative number, right? The width cannot be negative. So actually, x equals 20/3 is extraneous, not a valid solution. So I'm really just interested in x equals 2. So what else was I asked for? Find the dimensions of the box. Okay, so I have the x. So I guess this is the height of the box, right? So then all I still have to do is I have to get the length. That one was 16 minus 2x. And the width, that one was 10 minus 2x. So that's pretty easy. So let's see. The length, 16 minus 2 times 2 is 12. And the width is 10 minus 2 times 2, so 6. So the dimensions would be, let's see, let's do length times width times height. So 12 by 6 by 2 feet. So again, I was just going to show you one last step here, which was, well, remember our goal was to maximize. So let me just verify that x equals 2, that was our value, is a max and not a min, which is our suspicion anyway. So I'm going to do that by finding the second derivative. And then I'm going to say, well, if I plug 2 in my second derivative here, let's see, I get what, 48 minus 104? It's less than 0. So the graph is concave down at x equals 2, like so. So again, I verified, indeed, I have a max. So this all looks good. And just one more. Here we have a can, has a volume of 54 cubic inches. A can is a right circular cylinder. What radius and height would require the least amount of metal to construct the can? And then in this one, I actually have two formulas given. So that makes this pretty easy. So let's see. Pi r squared h, that's my volume. I know that's 54. Okay, what else does it say? Okay, so if I'm interested in the least amount of metal, then I guess what I'm really looking for here is I'm looking for how can I minimize. If I want the least amount of metal, I'm really trying to minimize the surface area. So down here, I have the formula given for the surface area. So that's just 2 pi r squared plus 2 pi r h. So this formula kind of makes sense because, well, pi r squared is the area of a circle, right? So there are two of those. And then this guy gives me the area of this portion. Okay, if I was to actually roll that cylinder out, I would actually have a rectangle there and its area would be given by this. But in any case, my goal is then to minimize that equation. But again, I have two variables. So same story. Substitute. Okay, so let me solve the first equation for, say, h. So h is 54 over pi r squared. And then I'll substitute that in here. So I'm going to have 2 pi r squared plus 2 pi r. And then my h is 54 over pi r squared. Let's see, pi's cancel. One of my r's cancels. So what will I have? 2 times 54, 108 over r. Or if you like, this is what? 2 pi r squared plus 108 r to the negative 1. Okay, so if my goal is to minimize that guy, then I have to find the derivative, right? So s prime of r, so what is that? 4 pi r minus 108 over r squared. So do an LCD. So what is that? 4 pi r cubed minus 108. over r squared. Okay, so then let me look for where that derivative is 0. It's really just going to give me the numerator equals 0, right? So what is that? 108 divided by 4 is 27 over pi. So let's see, the cube root of 27 is 3. So is it 3 over the cube root of pi? And then what else was I asked for? Let's see, let's go back to the problem statement. It says what radius and height. So I guess I still need to come down here and I need to get the matching height. So here's my equation for height. So now that I have my r, I just need to get my corresponding h. So to do that, I'm looking back up here at the h equation. So I'm going to plug my r in. I'm going to see if I can simplify it. This is going to be a little ugly. So it's 54 over pi. And then my r squared. So what is that going to be? It's going to be 54 for pi. That's 9 pi to the 2/3. It's 54 over 9 pi over pi to the 2/3. So flip and multiply. So let's see, 54 divided by 9 is what, 6? And then let's see, let me look at these guys, the pi's there. So I have pi to the 2/3 over pi to the 1. So 1 minus 2/3 leaves me with a third. And then the bigger power is in the bottom. So it would stay in the bottom. So it'd be 6 over the cube root of pi would be my height. And then for my units, I need to make sure I put those in. So those would be inches. So here are my answers then. My answers would be, here's my radius, here's my height. Those are my exact answers. Now, the end here again, I want to just double check that the r that I found is a min as opposed to a max. So to do that, all I did here is I just looked at my derivative. Where was that? It was right up here. I went ahead and found the second derivative. And then I said, well, for my r value, I have a positive r value here. So if I take a positive value of r and plug it in here, this whole expression is positive, right? So if that whole expression, if that second derivative is positive, I know the graph is concave up, right? So indeed, I know I have a min as opposed to a max.